think we're live now. Sitting down again with you. Gonna be good times. So this week, I feel like I'm still on my Advent of Code nonsense. I haven't given up yet, that's for sure. Trudging along. Let me know, some people were saying the mix last week wasn't so great on the audio. Let me know if this is good. So, yeah. Still doing the Advent of Code, keeping up this year. I got a little discouraged around day 4. It's a pretty tough one. Not hard, it was just a fair bit of work. Well, maybe it was hard, I don't know. But, I got caught up on the weekend, and I'm behind again. I'm going to probably end up doing problem 17 when I run. And today's day 8, so who knows if we'll get caught up. Who knows. But, so if you're already done 7, then there's going to be no spoilers here for you, of course. So, hooray for you. If you're on day 8, you're ahead of me. So let's just start with a quick review of what I worked on and some of the problems. I think some of them are pretty cool. So last week we did, I think we were only on day 2. Or, yeah. The inaugural day 1 was actually on Tuesday, but we ended up missing that one. So we did day 2. And day 3, it's pretty alright. I think that one was here. So these toboggan sled things. For those of you who don't know, or just watching this just because, maybe on YouTube, they show what Advent Code is. The idea is that you're going to start off in this little corner here of the map, and you're going to move down and to the right some amount of steps at a time. And they want you to count these characters here, how many times you hit it on that slope. The idea is that these are trees, this is a hill, you're going tobogganing down the hill. So you have an idea, or you got a miss, a hit, a miss, a hit, so on and so forth. My puzzle answer ended up being 198. And then you just test a bunch of different slopes. So this puzzle wasn't too hard. It was a little bit challenging in that it took me a little bit of while to figure out how to index into the appropriate column from the row. I'll show you that code in a second here. That's what this is over here. But I eventually figured it out. Taking the modulus of our, kind of like using vectors, direction X, direction Y. So for the index here is the rows. Probably misnamed these a little bit, but anyways, the idea is that you can combine these out, I guess, on a single line. You can use the mod, make sure that you don't go out of bounds and index outside of it, and figure out which row and column you're on, essentially. So that's what cycling's doing there. I was just making sure that we double up this, so if we go around, we wrap around. That's pretty much it. It's just figuring out indices. Day 4, I think, was the most interesting one for me so far. Again, this was the tough one. But I like the way the solution turned out. I really like it. So the idea is you just had to parse this data out. Birth year, issue year, blah, blah, blah. And there's some rules about what's valid and what's not. And you're supposed to write a function that determines that a given passport's valid. It was a little bit tricky. Not too tricky, but it was pretty tricky to parse the format, because the key, they come in key value pairs like this. They can be separated by a space or a new line. So like there is a new line one, another new line one, a space separation, so on and so forth. I forget why. Oh yeah, those are a little bit tricky because they're the double line thing, separating the individual passports, and just learning more about attoparsec and using it in Anger. That's how you kind of learn these things. So I struggled with it, but I kept up at it, got a good night's sleep, and figured it out the next day. This one, well, I'll show you the code. I actually ended up setting myself up really well to solve part 2 pretty easily. So the parser, pretty tricky. I'll show you the types first, actually. This is probably a better way to to see how I modeled it. So I didn't start out this way, but I ended up going with a higher kind of data type for my passport. So each of the fields could take their own types. Originally, when I was doing part 1, I just started out with these new type wrappers over text. But when I did part 2, where they wanted more validation rules, I just had to change the inner type of the new type wrapper, which was nice. But then I was like, well, should I use 2 different passport types, like a more valid passport type and then the regular one I started with? I said, no, this is Haskell. I should be able to have my cake and eat it too. So I made it into a higher kind of type. And then that way I could create just a text passport, and I could create a valid passport. Pretty nice, I think. So using that same parsing code, I was able to fill in the 2 different types, which is kind of good. So things I learned doing this parsing here. I think just I kind of forget now what I learned here, but there was something about structure. Oh, parsing the whole file. Something about structuring it so that I always have I can parse by like chunks, and I always have a separator with many one, and then I have like some parser that takes a chunk and parses it, like maybe the whole line usually. This one was a little bit tricky because, like I was showing you, it was the space or end of line thing. EOL or space parser created for that. I ended up learning a little bit more about this operator guy in later on at some point. But the lesson for this guy is that this is it looks like OR, and it is kind of like the OR. Like there's 2 parsing branches here. If this one on the left fails, that's okay. This OR one's just going to try this one. And I think the way it works is that it's not going to consume that input if it fails. It's going to backtrack. Which means that this is not like your typical OR. It's the order matters of which. That makes sense. The order matters which parser you try first. Come up probably later. But I use it a bunch here just to parse those guys. Yeah, into their passport keys. What else was cool about day 4? Using Reload. I used Reload a fair bit here. So once I did the first part, it was a matter of I ended up using, actually, this is kind of an interesting idea. You probably saw it in the parsing code, where I'm parsing the passport section And you notice the key and values can come in any order. I used a data structure where the orders don't matter, and took some assumptions with that. The assumptions being that the key value pairs don't appear twice. They're unique. Otherwise, we're kind of bound to, I think I made a note of that in the parser, we're kind of bound to whatever choice map.fromList uses for when it detects duplicate keys in the input, which I think just takes the last one that it sees. So, or maybe it's the first one, I don't remember, but either way, you're kind of beholden to that if you go with this approach. But it worked out fine for this puzzle. So it's just a bunch of map lookups for the keys and the values to construct the passport. The second time through, same structure. Just use monadic bind to pass into the validation function. The validates this like kind of like smart constructors that go from text to my types. Which is where I kind of use some of these functions I use with reload. So what I like about this is super sweet and really, really cool. This is an enum. It's a very common thing to do in a lot of programming languages. And we kind of like to have bidirectional parsers and serializers. It just makes life convenient. And the problem I find sometimes with writing parsers and serializers for your types is that you have to write code to handle them. You have to make sure you handle all of the different cases. And most importantly, later on, when you change this enum, somebody else changes this enum, or you later on, you have to remember to update all your parsing and serializing code. Okay. Haskell does help a lot with that and does make it easier to do in general. But this nice little pattern comes from Reload and Koinik. They have a little extras library with Reload that handles stuff you can do with, specifically with bounded enums. Maybe just enums in general too. But it has this nice handy dandy function, inverse map. So when we're parsing an eye color from text, we have maybe eye color. And normally you can imagine if you're writing this out yourself, right? You would have a bunch of cases here where you'd match all the different strings that are valid. You can parse into these constructors. And then you'd probably have a blanket catch-all one, right? And that's a potential source of error in Haskell code. Because that blanket catch-all one is the blanket catch-all for any string. So if you add a new case here, you won't necessarily get warned about it in your parsing code. But this solves that problem. It's not going to be good for, and if you look at the implementation, you'll understand why, but it's not going to be good for really large, like enormous enums. But for small ones, there's a small performance hit, but it's not going to really matter to you in application code most of the time. So what it lets me do is that I don't have to define that catch-all sort of semi-partial pattern match. This guarantees that it'll be handled. So when I add a new case to say eye color, for example, the pattern match here will be incomplete, and I'll get warned about that. So I add a case here, and this one's automatically taken care of by inverse map. Pretty nice. So just have a bunch of smart connect. So it's a cool pattern, and then I just have a bunch of smart constructors that validate all the different rules that you get from the puzzle, and Bob's your uncle, and you get this nice passport type. That's correct by construction, or parse don't validate, basically. So I don't actually have like a validation function here, because this will parse it into a valid type. So if it manages to parse, then it's correct according to the rules. You can't construct a value any other way. I could be very, very restrictive in my module and just not export the constructor for passport, for example. But I don't know. The Python in me, the Python programming for a long time ago, was very permissive with my modules. I don't know. I work on code bases now where explicit is the way to go. Explicit export lists. And that's fine. You know, you stick to conventions of the teams you're on. I personally don't like it all that much. I find it annoying to have to deal with them, because then you have to do here, have to do here, but there's trade-offs, right? Like if you do this a lot and you have a lot of conflicting names, it can get pretty annoying, so. Anyway, I'm getting sidetracked. That's day 4. Day 5 and 6 were, in my opinion, pretty simple by comparison. They're kind of a breeze to get through, for me, at least. So 5. It's just a little bit more. The parsing on this one was super easy. The only thing I thought interesting about this one was, so basically brief problem description. You got like a space, like you can imagine a grid, a certain amount of rows and columns, and these symbols, F and F and B, stand for front and back, or which half of the space to partition on that you want to keep. You just partition through the whole thing and find a single value for each, which made me think of that this might have a fixed point. And this function would be a fixed point on a tuple. And that'd be an elegant way of describing it and solving this. An interesting way, maybe. Maybe not elegant, I don't know. I took a pretty straightforward approach. I parse the C codes from text, and then I just have a simple find seed ID. Function is probably the best way to do it, maybe, for me. So I just do a recursive binary partition, dividing by 2 every time you capture the symbol. This code's a little bit, I mean, it's not the greatest. I mean, this case will probably never be hit because of these, but you never know, so you have to put it in there because Haskell. Basically because we return in these cases, so this technically should never get hit. But, and also because C code will prevent it as well. So, yeah. Pretty straightforward. Not too much to see there. Day 6 was kind of the same. Day 6. What was this one? This one was a similar parsing issue with day 4. So I had some experience with day 4 to figure this one out and get through it, but I did it. The idea is that you just want to collect the sets of answers for each group, and each group is these collection, again, separated by lines. Or these are separated by lines. Each line is one set of answers, and you want the union, the set union of the answers for part 1, and then part 2 is basically you want the set intersection of those. Take the sum of the length of those sets, which is basically how I solved that on 6. I don't know why, that one just stuck out. That was pretty straightforward to me. Right, so I solved that. I solved it back in module, which is a kind of the pattern I've been taking with these. Alright, so the first one was just union. The second one was intersection. The only interesting, notable thing I think about this code is that I did end up using non-empty here, which Prelude is kind of promotes a little bit, using non-empty over list, or at least preferring it. When you mean, because often you mean non-empty lists. At least that's their philosophy, which I think is an interesting one to try out. And it worked out here pretty well, I think. So because I used non-empty, adding the intersection function was pretty simple because when I first attempted this, I did what I did with union. I naively added set.empty. And then before submitting my answer, I looked at it and was like, this is not enough. So it's like, oh, I need to put a base value there for intersection. Is this part of the function signature? I need a base set. What am I going to put there? I can't just put empty because the union of the empty set is going to be always the empty set. And I was like, wait a second. I have a set to put to start kick us off with this fold. It's the head of answers. It's just guaranteed to be there because it's an on empty list. So that's kind of the only interesting thing for problem 6. So it made this code kind of nice, pretty straightforward. So yeah, that's caught up now. We're on day 7. Let's get cracking. I have looked at the problem description for day 7. So this one, we've got these bags. One light right bag contains one, contains this. Some can contain no other bags. This is going to be a pain in the butt to parse because there's bag, there's bags. There's this case here, no other bags, since for the empty list things. But because of the question, how many bag colors can eventually contain at least one shiny gold bag, right? And that's what we're kind of like starting with. So you want to find out how many the number of colors that can eventually contain at least one shiny gold bag. This one to me, when I first read it, looks like a graph problem. So I don't know if you've seen graph problems before, but if you can look at, say, light red bag, right? Light red bag. It can contain one bright white bag, uppercase convention, then lowercase, and muted yellow bags. Now, knowing these problems, I think these numbers are going to be pretty important. Like, probably going to go up there, I bet. I have a sneaking suspicion this is going to turn into like a weighted graph or a counting graph problem. All right, but if we see, let's see, light red or dark orange, bright white, muted yellow, shiny gold bags, dark olive, light color. So this one, muted yellow, I think is another one we saw here, right? Yeah. So from muted yellow, we get muted yellow bags can contain shiny gold and faded blue. Right. We also saw shiny gold bags can contain stuff. Okay. And these might, I don't know if it's going to be, I think it's directed. Because the idea is that we want to find how many can contain. Bags contain one. So I think they might be directed. If you disagree with me, chat, let me know. But I think they might be directed. Which means the edges go one way. All right, I'm gonna have something here, something here. So the question becomes, say that this is a shiny gold, right? We're starting with shiny gold. This guy here. We want to find out what bags can eventually contain this one, right? Yeah. Contain at least... How many bag colors can eventually contain at least one shiny gold bag? Alright, so starting there, we're going to want to look at basically all the other bags. This one, well, given our problem description, yeah, muted yellow can contain a shiny gold bag. This one up here contains a muted yellow bag, which can contain a shiny gold bag. So this one could be in our set. Now, this is the reason why I think it might be directed, is because if this was undirected, we could go from brown bag to light red bag to emerald bag to da-da-da, but I don't think we might not have a description that says brown bag contains emerald bag, right? So that's why I think they're directed there. Otherwise we could finding all they'd all be connected to this one. And then all of the bags can contain a shiny gold bag. So, that's directed graph. So we have to find all those ones that shiny bag is in the set of as an ancestor of these. We're also going to need to parse this silly format. And I kind of have some ideas about how we can tackle this. Right. I think ultimately when we get there, we're going to basically visit. We're going to get a list from this, right? We're going to get a list of this with a node name and its direct descendants. And we can basically, I think this is a case where we can use some dynamic programming to solve this one. It's like depth first search, but we could do dynamic programming. Because we have this list of descendants, we could store this in a map. Right? One node has a key in the map, and then the set of all the potential ancestors. Yeah. So then we go look this one, we look at potential ancestors. Doesn't really matter. And we just collect together. We'd have to traverse like everything to get it, but we could start here and look at his direct ancestors. Is it shiny gold? No. So we put it on our search list to visit these two ones. We visit this one, get its ancestors. Does it include shiny gold? Yep. So that one's a potential. There. So on and so forth. And we would just keep recursing until we go through the whole thing. Yeah. Well, let's parse this stuff first. This is going to be the most annoying part of the whole process, and I generally start off with this population.
As such, main force patrol, an outrun police force, has been created to patrol the lands and to uphold the remains of law.
Let's get our puzzle data first. Yes. Need our input. Need on us. Plenty of input. Data. 2020. Day 7. That test. Right. Let's write parsers, friend. 2020. Day 7. Nice. It's kind of the convention I've been taking lately. Advent, year 2020, day 7. Where? Adjust this here. Second. There we go. I'll make it easier to type without doing this. Okay. I'm gonna write a bag parser first. I'm gonna import data parser. Usage experience reports is out of parsec. It's a pretty low level library, mostly built for speed rather than nice error messages. So if you're looking for nice error messages and integrations with better libraries, there's a library called megaparsec that a lot of people recommend. Also very good. But I've found some tricks with working without a parsec as I've gone along and done a few of these problems. And maybe we'll encounter them. Right. Usually I like to start with types, and I don't know if we're going to use anything more interesting than primitive types for this one. Just because there's not anything terribly interesting. Oh, the data here? Maybe we could do like... Oh, well, maybe we'll just do a couple of like, type aliases or something. Just to give us something to work with. Day 7. Text. The different, there's a lot of, I mean, we could parse out, figure out what all the unique color combinations are. I'm sure there's quite a lot though, and maybe I'm shooting myself in the foot, but I'm just not sure that it's going to be worth it for this puzzle. So I'm just going to leave it as text. And main list contains basically just a list of int and bag. Not very interesting so far. It's okay. Okay. Actor. Okay, so we create a bag parser. Parser of bags. This one. Just want to get the name up to this terminator. Now what's tricky about this one, I think, as we noted at the beginning there, was that it's bag or bags. So we're going to figure that one out. Shouldn't be too bad though. I think they're all just, since it's text, we can just take any character, really. Any valid text, and we just terminate the parse when we get to that end condition. So let's do mini car up until finally the string bags. String bag. I thought that would that's another parser called .text maybe. Yeah, it's going to want text, so we need to import qualified .text and just fmap over the parser our text wrapping. Text.pack. That should do it. One thing, a common mistake I commonly make when I'm doing these challenges is that I get too excited about starting the puzzle and getting it done. And I forget to write tests. Which has bitten me a couple of times. Especially on day 4. Like, once I got a good night's sleep and I started writing tests and just slowing down and thinking about it and just being careful, cautious, things went a lot more smoothly. Like, a lot. So I'm going to do that here. I think that's the main thing I've learned about doing this challenge and keeping up with it is sleep, tests. Even if it's just 1 or 2 as a sanity check. Nothing big. You don't have to be super thorough. Okay, 7. Yes. So let's describe parser. Parse a bag. That's what it can do. Let's just take an example straight out of our input. That also helps a lot. Let's just put a little space on these. Because why not? Yep, so then we get that. And then we can do parse only the bag B. Input. This is in the right